Welcome to Spring LIB.
Okay, the reactions that we need to know to answer this question are what does potassium permanganate with sulfuric acid do to derivatives of benzene, right? Because we're given C9H12, and if we plug this into our double bond equivalency formula, we get number of carbons minus the number of hydrogens divided by 2 plus 1 equals 9 minus 6 plus 1 equals 4. We're told that we have 4 double bond equivalencies, which means we have either a total of, if we count up the number of double bonds and or rings in our starting material, we're going to get 4. And when I see 4 double bond equivalencies, the first thing I typically think of is benzene. Right? Benzene has 1 double bond, 2 double bond, 3 double bond, and a ring that gives a double bond equivalency of 4. That's very likely when you calculate a DBE of 4 that you're dealing with benzene, right? It's not a guarantee, but the other hint that we're dealing with benzene is that they start telling us that they're going to react our molecule A with KMnO4, lowercase n there, and H2SO4, and then we're going to get out some kind of acid. Okay. Well, it turns out that if you take alkyl benzenes, so here's an example of one, and react them. I'm gonna stop writing H2SO4 just for time purposes, but I'm just gonna say potassium permanganate, that you get out a carboxylic acid, or in this case, benzoic acid. Why do I think we're making this? Well, because we're told that we're going to take whatever product we get out and we're going to neutralize it with sodium hydroxide. Okay. So we're probably making some kind of acid. Okay. That's where my logic is going here, right? So let's go back to the fact that we have C9H12, right? And we're assuming maybe it's some kind of benzene derivative. Great. Well, now we've got 3 more carbons to tack on, right? So we could do something like this. We could do something like this, right? But how do we know? Well, we get another bit of information here. For one, we can find out how many moles of C9H12 we started, and we can find out how many moles of sodium hydroxide it took to neutralize the acid that resulted from our starting product. So it may not be immediately obvious, but the molecular weight of C9H12 is 120 grams per mole. And we were told that we have 1.2 grams of our starting material, which, if we divide by 120 grams per mole, tells us that we had 0.01 mole of our starting material. It also means, assuming that we had a total conversion of our starting material to the acid, we had 0.01 moles of acid. Now, in terms of neutralization, they told us that it took 200 mils, or 0.200 liters of sodium hydroxide, or base, at a concentration of 0.1 molar, right? So it took 0.02 moles of base to neutralize our acid, which tells me that every acid molecule we had must have had 2 distinct OH groups, or carboxylic acid functional groups. So it's more likely that we had something like this, right, with 2 alkyl groups. Because if we had 3 alkyl groups, then we should have expected to have 0.03 moles of base required to neutralize it. So this is much more likely an ethyl and a methyl. Okay, so now we've got to decide where to put that ethyl and the methyl, right? So let's look at this. Right, we can say methyl ethyl. We could say methyl ethyl, or we can say methyl ethyl. Well, now we're looking at our final bit of information. The structural formula and the name of compound B, according to IUPAC, is known to have two different monochloro derivatives. What's that mean? Well, it means if we take this structure and add a chlorine to it, after we've converted it to carboxylic acid at this point. So recall that we're going to take this and then react it with KMnO4, and we're going to get instead right, we're going to get carboxylic acids. So after doing that, if we react this in a way that adds a chlorine molecule, there are exactly two distinct ways to do that, right? So the question is, like, if I add a chlorine here, is that distinct from adding a chlorine here? That's kind of the question. How many unique positions are there on this molecule, right? So this molecule is actually symmetric, right? So this location is the same as this location, and this location is the same as this location. Maybe I should color code these blue. So I see two distinct monochlorination products here. Let's look at another example. This molecule here, we've got symmetric line there. So this is a possible monochlorination, which is different from this possible monochlorination, which is different from this possible monochlorination. So there's three possible monochlorination products here. Finally, we've got symmetry here. Okay, so we could have monochlorination here. Actually, the problem here is that we've got symmetry twice over, right? So this is the same as this is the same as this is the same as this, right? All monochlorination products of the para, right? So that these are related ortho, these are related meta, and these are related para. All the para monochlorination products will be the same. There's three different meta carboxylic acid monochlorination products, but this ortho one is perfect. So I'm going to walk through this logic front ways now. So this was kind of deducing how I knew that this was the product, but now let's see exactly what they're talking about. Okay, so basically what they're saying is we had this product, right? And we had 0.01 moles of it. And we took it and we reacted it with KMnO4. And that gave us this carboxylic acid. Okay. And so we had 0.01 moles of this. And to neutralize it, how many moles of base do you think it would take? to deprotonate all of these carboxylic acids? Well, if we had 1 mole and there were 2 acids, 2 OH groups, then we should expect that this would take 2 moles, or 0.02 moles. Right? And then finally, what they're saying is if they took this molecule and monochlorinated it, that would be Cl2 with AlCl3, that there are 2 possible products that you could get out. You could get this product out. Or you could get this product out. And what may not be immediately obvious is that you could also add a chlorine here, which would be equivalent to where I've drawn it, and you could also add a chlorine here, and it would be equivalent. Okay, so that's the whole idea of the problem. So the structural formula of A is this.